couple more things to say about 1.1. I guess it's, yeah, 1.1. I've already started dabbling a bit in 1.2 by talking about domain and range. And I'm going to dabble around a little bit about 1.3 as well. So I kind of talk about everything simultaneously. So hopefully that doesn't confuse your notes. But before I erase these, in 1.3, we talk about some more properties of a function. Regions in which the function is increasing or decreasing. Okay? Some functions might be increasing for a certain area of the graph and then decreasing for another area of the graph. But in any case, whenever I say the words increasing or decreasing, it's understood that I'm meaning as you scan from left to right. Make sense? So for example, before I erase the square root function, I would classify this function as a function that is increasing. Yeah. As you scan from left to right, it starts at 0 and starts to go up. And it keeps going up. So I'd say this is increasing over the interval that begins at 0 and goes all the way out to infinity. Now in this class, I'm not going to be super picky about whether you use a round parenthesis or a square parenthesis right here at this particular point. And that's because it's debatable. Like, what actually is happening at the end point? Is it, you know what I mean? It's, I don't know, we'll leave that for the philosophers to argue over, but I won't be picky on that kind of a detail on the test. So when I'm describing intervals in which is increasing or decreasing, I'm pretty much just using round parentheses. I never use square parentheses. If I ask where is the function decreasing, the answer is going to be, it's easier just to say it with a word, nowhere, never. Or in set notation, you just say empty set. That's the set with nothing in it.
So there's a difference between a zero line through and a 0.
Yeah.
Okay.
Yeah, a lot of people will use like put a line through it to indicate that it's a 0, not to be confused with the letter O, right? But in math classes, this symbol is used for the empty set, not for the number 0.
Yeah.
Okay. Is that a military thing?
Yeah.
Okay. I had a feeling that was the case. And regarding the cube root function, in this case I'd say it's increasing from where to where?
Negative infinity to infinity.
Yeah, pretty much everywhere. It can't be both increasing and decreasing, right? As you said. How about the inverse square function?
Increasing from negative infinity to, that's it, maybe 0?
Yeah. Yeah, certainly not at 0 itself.
Yeah, but,
Yeah.
and then 0 to infinity, decreasing.
Again, these are not the sort of things that you should have to memorize and make flashcards for. If you, given the picture of the graph, it should be self-evident. with practice, I should say. Maybe not self-evident, but with practice, you'll be able to see it quickly. Yeah?
Because we had empty set. What shows decreasing? How do I know that that one's decreasing?
You can tell because if I start at 0, I mean, I guess technically not at 0, but just to the right of 0, just to the right of it. As I scan from left to right, you can see how the graph is going down. If the graph is going down, then it's decreasing.
Like, you have 2 arrows at both ends.
Right, yeah. See, and that's why, yeah, see, like, when you see this arrow right here, I think this is what confuses people, is they're like, well, it's increasing. It's going
Yeah.
up. Which is why I said specifically from left to right. If you're going from right to left, then yeah, the graph,
Okay.
this branch of the graph is increasing, sort of.
So when we're looking at, like, I guess you said section 1.3, so rates of change for increasing, we're reading it from left to right.
Yeah.
Okay.
So if I say it's increasing, even though I won't necessarily say it, that's just like math vocabulary. That's just how mathematicians talk to each other. It's understood that we mean from left to right.
And it decreases from 0 to.
Mm-hmm. Yeah. So you want to avoid that pitfall. Just because the arrow is pointing up doesn't mean it's increasing. Where is the constant function increasing?
It's not.
Right. This is another debatable one, but in our class, we're just going to say it's not. For the same reason. It's neither increasing nor decreasing. And you can, for the other 5 toolkit functions, just based on the graph, you should be able to identify where it's increasing and where it's decreasing. I'm going to leave that for you to do as an exercise. I think it's in the book as well, in case you're not sure. But yeah, if you go through the other 5 toolbox functions, you should be able to express with interval notation where it's increasing and where it's decreasing. Okay. And that would be a fair question, I think, next week on the exam. The final function I'm interested in is, I think it's what the author calls piecewise functions. I personally, especially in the fall quarter, I like to call them Frankenstein functions. It's where you can kind of chop up functions and put the pieces together to make a new function. I'm about to define a piecewise function. All right? Let's say it's how about what do I want to say?
What is that? Is that supposed to be greater than or equal to?
Yeah,
Okay.
greater than or equal to. The last one you mean?
Yeah.
Yeah, I think that makes sense. And go on from there to there. Okay. So this is a piecewise function. It kind of has some conditions associated with it. So let's see, I haven't really told you precisely what I mean by this, but I think if you were to take a guess, you'd be right. What is f of 0?
It wouldn't work with constant 1, 3.
Right. I would only do this if the input was greater than or equal to 1. Since 0, the input in this case, isn't greater than 1, I'm not going to do that.
You wouldn't be able to do any of them.
I think we can do one of
What's
them.
that?
You can do the first two.
Oh,
Because 0
you do that one.
is in between -1 and 1. But 0 is not less than -1, right? So you have to, in a way, piecewise functions are kind of weird in that you have to kind of like read from right to left. You notice that? The important information is over there on the right. If I want to know what f of 0 is, I have to first figure out which set of instructions to follow. And if x equals 0, because 0 is between -1 and 1, these are the instructions I'm going to follow. In this range, the graph will look like the identity function. But in this range, the graph will look like the constant function. And in this range, the graph will look like the cube root functions. Even though we only have 9 toolbox functions, you can actually, manufacture infinitely many types of functions, right? You start doing things like this. And when it comes to piecewise functions, it could have like 5 or even a dozen different pieces to it. Anything's possible. But yeah, so if the input is 0, then the output is the same as the input. So therefore, f of 0 is
0.
And therefore, moreover, f of 1
You can only do read.
yeah, it's almost in this region,
It's not
but it's not equal to it. So because of the greater than or equal to, I would say that the f of 1 is 3. Right?
There's a closing bracket or anything on the right side of the function.
Where?
In the function how it's written out, you have f of x equals and then an opening bracket dealio.
Uh-huh.
There's nothing that closes it out on the far right side.
Oh, this one right here? Or right here? Wait, what?
No, he's saying as a whole.
Yeah, as a whole.
He's saying the set of numbers
Immediately after the
bracket,
equal sign.
your set of numbers bracket?
Yep. It's not a bracket, I don't know what it's called.
You
Oh,
open
this like
Yeah, that
sort of
dealio.
Yeah.
squirrely
Yeah.
bracket? Yeah.
There's nothing that closes that out on the right side.
Oh, I see what you're saying.
Yeah.
Right. Yeah, there isn't.
Okay.
Yeah, it is actually, it never occurred to me until now, but it does look like that set notation that I was using earlier, doesn't it? So I was using curly brackets for that one too. But yeah, in this case, no. No, when we're doing piecewise functions, we just use this to indicate that there's like, that all 3 of these are part of the same function. But yeah, I suppose, I don't think I'd take off a point if you put a close bracket right there. But this is standard in all math classes. Okay? Yeah?
So if I did f of 2, would that also be 3?
Yep.
Okay.
And why is it 3?
Says- Oh, because is this the constant?
Because 2 is bigger than 1. And when 2 is bigger than 1,
It's 3.
that third set of instructions are the instructions we follow.
Fortunate? Maybe none. Can't do it.
Yeah. So you kind of scan through each of the 3 possibilities and ask yourself, is -1 less than -1? Yes or no? All right, move on to the next one. Is -1 between -1 and 1? The answer, no. Is -1 greater than or equal to 1? Answer is no.
Maybe undefined.
So it's undefined. So 1 is not in the domain. Oh, sorry. -1 is not in the domain.
First one?
Yeah. -8 is in fact less than -1. Therefore, I'm going to follow the first set of instructions. Since -2 times -2 times -2 is -8, then that too is a point on the graph. That too is, that's what the -8 maps to. Believe it or not, this is actually some of the most important ones in real-world applications. Programming, sure. If you ever get like a electric bill or a gas bill, a lot of times they have several tiers. You ever see like tier 1, tier 2? You know, if you use within this much energy, like they charge you at a certain rate. But then once you go to the second tier, they start from that point forward, they start charging you at a different rate. That would be an example of a piecewise function, right? Or if you're like a mechanical engineer and you're studying like you're designing like engines, you know, the manual stick shift sort of thing. Like if you compare the speed to the RPMs, you know, when you switch gears, all of a sudden the RPMs change very abruptly. So piecewise functions would be a very useful way to quantify what's going on there. Now here's the interesting part. I wonder what the graph would look like. Now this is a question that could appear on next week's exam, and I think if it does, it'll probably be one of the hard ones. Okay. Can you graph this function? Now the graph of this function, there's a lot of like pitfalls there. So it's easy to lose a point here and a point there, just for like really subtle details. But we have already 4 points at least that I can put on the graph. You can see already that f of 0 is 0. That is to say, when x equals 0, y equals 0. I can also see that when x equals 1, y equals 3. This is also a point on the graph. And when f equals 2, again, y equals 3. We saw that when the input was -1, there was no output. So in our final draft, we're working our way up to the actual final draft of the picture. But when we get to the final picture, you're going to see that if you look above this point and below this point, you will not see a point on the graph. Okay? So just keep that in mind. And if the input is -8, then the output should be -2. 2, 3, 4, 5, 6, 7, 8. 2. So we got 4 points on the graph. If this question is asked next week, that would be enough for partial credit at least. Better than nothing. Can we fill in more detail?
So that'd be a cube root function?
Part of it's a cube root function.
Okay.
Part of it's the identity function. Part of it's the constant function. So you know that the identity function's a line. Actually, so is the constant function. The key is, where does the line begin and end?
It doesn't, arrow.
Yeah, I would use an arrow if the line just keeps going. If it's not clear yet, keep picking numbers, some positives, some negatives. Maybe even some fractions would help, I think, in this case.
It's an increase.
From where to where, though? It might be good to do some scratch work to the side just to remind yourself that if y equals 3, then the graph looks like this. And if y equals x, then the graph looks like this.
Wait a minute.
And if y equals cube root x, then the graph looks like this.
If it's from 0 to infinity, it's a constant, because anything greater than 1 is sum 3.
Right, yeah.
So it increases all the way to 0, and then it stays constant.
So if we didn't do it yet, but if we had plugged in 3, we'd get 3. If we had plugged in 4, we'd get 4. And eventually you're going to convince yourself, hopefully, that this part of the graph is going to be a horizontal line. Where does that line begin and end?
It goes on forever that way, and it starts at 1.
1 infinity.
So you would put an open circle at 1.
So it starts at 1. And you're saying you want to use an open circle?
No, it's close because it's equal to.
Yeah. So yeah, so you see what I mean, how there's a lot of pitfalls. You might have the basic idea, but there's some subtle points, little points here and there. The question is, what about this point itself? If I use a filled in circle, I'm saying that if you plug in 1, you get 3. Right? And we saw that if you plug in 1, indeed, you get 3. You do get 3, and that's because of this greater than or equal to symbol, right? So it is appropriate to use a filled in circle. Now sometimes when I'm in a testing situation, I think everybody feels like a little insecure. Like, I think it's this, but I'm not sure. So they'll make it filled in, but it's kind of tiny. If I can't tell, I might take off a point anyway, even though it was a filled in circle. So kind of exaggerate it so it's clear whether you're committing to a filled in circle or an empty circle. If I can't tell, then I'll take off a point. Okay. So it's still unclear to me what's happening between 0 and 1.
Is that increasing?
It's increasing. How do you know?
Left and right is going up.
Yeah, because you know that the identity function is increasing. And from here to here, between 0 and 1, we're following these instructions. In fact, from -1 to 1, we're following these instructions. So I just want to give you a chance to stare at it. I want to make sure you can see what I'm about to draw before I draw it. If it's not crystal clear yet, you should be thinking, what is f of 1/2? Since 1/2 is between -1 and 1, then f of 1/2 is
1/2.
what's f of 0.9?
0.9.
What's f of 0.99?
9.
Or f of 0.999? And yet, the moment you get to f of 1, the graph leaps all the way up to 3. Kind of an unusual graph. But at least up to, but not including 1, it'll look like the identity function.
To get full credit, we'd have to do that.
I'm not done yet, though. F of -1 is technically undefined. But f of -8 is -2. How about f of -2?
That would work. So would the line just break off? Be my guess.
Kind of.
Because it's not main.
Mhm.
So it kind of do what's called the inverse like square function.
Oh, yeah. Well, it'll, without a doubt, it'll look like this,
Okay.
because that is the formula we're using, right? But, so what I'm about to draw is going to look identical to what you see over here, but only up to a point, right? So notice that -1 comma -1 is a point on that graph. The cube root of -1 is -1. So I'm pretty sure that the graph is going to look, okay, it looks like a straight line, but it's technically a curve right there. And it's leading right up to that same circle. The two graphs kind of join each other. The two sections kind of join each other right here, although technically it's undefined at that point in particular. And I think that would be a complete graph of this particular piecewise function.
Would that point connect to, or would it just, no?
It would if there were points I could pick that would give me the points in between. But yeah, we won't be talking about that much in this class, but in calculus, we'd call this a discontinuity, right? It just kind of jumps. Sometimes that can happen. We won't be dealing with that a lot in this class, okay? But yeah, this is a tough one. You know, it's going to take, for most of us, I think it would probably take at least 15 minutes just to come up with this graph with all the details just right. Right? It's going to take some practice. You'll get a little bit of practice with that on WAMAP. They're not going to give you a ton of practice. I wish they'd give you more. Maybe someday I'll enhance it. Yeah?
I missed it somehow. How is, I know the -1 is undefined, but why up there do you have an undefined 1? 1 and 1, it looks like.
1 and 1?
Yeah, why is that
Ah.
undefined? Because
mhm.
according to this, x can be greater than or equal to 1.
Yeah, so it is defined at 1.
Yes. So were you just like
And
trying to
so-
show something?
That's 0.99.
Right. So if you if you didn't have this formula to look at,
Right.
and you only had this graph to look at,
Mhm.
and you're wondering whether it's defined at 1, then you would start at this point on the x-axis and you'd look up and down for a point that's on the graph. And you'd see that this is not a point on the graph. However, this
This
is a
one is.
point on the graph. And so because there's a filled-in circle here and an empty circle here, it makes it crystal clear that f of 1 is not 1, but 3.
Okay.
Yeah, so
But
just because there's an empty circle
Uh-huh.
doesn't mean it's undefined.
Okay.
It just means it might be defined, but whatever it is, it's not that.
Okay.
Yeah. And I'd say this function is increasing from negative infinity up to -1.
Mhm.
Stops for a moment,
Yes.
and then continues to increase from -1 to 1. And then it's
But
neither
but not
increasing-
including -1.
Right, yeah. And then it's neither increasing nor decreasing beyond that point.
Could we grab the domain and range for this?
Yeah, so if I had asked what's the domain of this function? So a lot of, so there's lots of questions I could ask. Maybe a word problem and say turn it into a piecewise function turn it into a graph turn it into a piecewise function. Lots of different mutations and ways to ask the question. Another reasonable question next week would be, what is the domain? What is the range? Where is it increasing? Where is it decreasing? Those would be 4 great follow-up questions. In this case, I'd say that the domain is everything from negative infinity up to, but not including. But that's not all there is
Is
to
it
it.
connected
Union.
to,
Mhm.
would it be 1 to infinity?
Well, not
1
yet.
to 1.
Actually,
Bracket.
I would just go ahead and just say infinity. Right? Because, 1's in the domain, right? Everything to the right of 1's in the domain, everything to the left of 1, I mean, to a point is in the domain. So that would be correct. And the range? Well, that's an interesting one.
Can I take a stab at this?
Yeah, go ahead.
So, be negative infinity to 1, or to -1, with parentheses. And then a union, and then parentheses, -1, comma 3, bracket.
Well, I would say no, because I can't find a point on the graph where 2 is in the range. You're close.
Okay.
It'd be just 3 would be united, right?
So, -1 is not in the range, but numbers really close to -1 are in the range. Like -0.99, there's a point right there with the y-coordinate of negative 0.99, negative 0.5, 0, 0.5, 0.9, 0.99.
So,
Mhm.
in the first one, would it be negative infinity to 1? Or,
Well,
it's not
only-
included?
I would say no, because I can't find any point on the graph that has a y-coordinate of negative 1. Think of it this way. At least in my mind, I'm imagining like a horizontal line that's just scanning upward. And I'm picking up y-coordinates along here until I get to negative 1. But then at negative 1, if I look to the left and the right, I don't see any point on the graph. So that's why we're skipping past negative 1. But if you continue past that point, I do see points on the graph that has y-coordinates that are between negative 1 up to, but not including 1.
So would you have 2 different unions?
Yeah.
Yeah, 3 in the squiggly brackets.
Yeah.
One would need a bracket.
Hmm.
No,
It
no,
would if
sorry.
we were talking
No,
about
we're
the
talking
domain.
about X. Sorry, wrong one.
Yeah. Yeah. A lot of subtleties. I said this one already verbally. Now notice that when we're talking about increasing, regions in which it's increasing or decreasing, I'm only using x coordinates to describe the regions, not the y coordinates. Does that make sense? So I'd say it's increasing from values of x that are as small as negative infinity up to.
Negative 1.
Yeah. I'm tempted to say all the way up to 1. It's just that it's not defined at negative 1. So. But past that point, it continues to increase from left to right. And then it stops there. It's no longer increasing.
So because negative 1 is undefined, you always have to break it off at negative 1 because it's undefined?
Yeah.
Okay.
Yeah. So I would never say it's increasing at a point that's not in the domain. It's nowhere decreasing. Yeah, admittedly, first week it's a lot of vocabulary and notation, just so we can communicate with each other on a mathematical level, at least. Okay. So 1.3 is pretty important. I think you could say, if I was to make a broad generalization, Math 151, also known as Calculus 1, is all about rates of change. So 1.3, we're just going to be spending a moment on it and passing by and moving on. But you could think of calculus as just staying 1.3 for a whole quarter. So, and I've already jumped ahead of 1.3. When we were talking about increasing and decreasing, these are terms that we use to describe the behavior of a graph. This is coming from the textbook on page 39, example 5. There it is. So yeah, the page 39 example, is that the same in your edition? Okay. All right, I don't think anybody has the physical book with them today. That's fine. It's right here. It says here the magnetic force measured in newtons between two magnets is related. Remember how I mentioned the inverse square function? I said it's kind of like gravity. The same can be said for magnetism as well. All right? So between two magnets is related to the distance between the magnets, d, in centimeters by this formula. So this is a function here. Looks like your inverse square function, except there's a 2 on top instead of a 1. Right? Find the average rate of change of force if it says here to find the average rate of change of the force if the distance between the magnets is increased from 2 centimeters to 6 centimeters. Right? And we are computing the average rate of change. Oh, okay. Oh, there you go. Okay, so again, magnetic force. So in this first sentence, they're describing the nature of this function, right? I can see that f of d equals 2 over d squared. And based on that alone, I can see that f of 2 is what?
What happened?
It's 1/2 because if you take the input and square it, you get 4. And 2 divided by 4 is 1/2. Is that what you were thinking? And that's pretty good. But a difficult problem goes from hard to impossible when you lose track of what the numbers mean. We got 2 numbers here. One of them's an input, the other one's an output. What are the units of that 2?
Centimeter.
Yeah. You might have to reread this first sentence several times, right? As you're, in order to interpret what we just accomplished. I mean, yeah, I did the math, but so what? You know what I mean? How does that have any bearing on the question at hand? This tells me that the magnetic force measured in newtons between two magnets is related to the distance between the magnets. So that 2 is actually the distance between the magnets in centimeters. See that? A lot of, on the exam next week, there's I mean, you know, I want to believe that everybody's going to get a perfect score. But most of the time that doesn't happen. Some people are going to make the mistake of thinking that this is 1/2 of a centimeter instead of this 8 centimeters. You know what I mean? It's easy to get those mixed up, right? This 1/2, the output, you should be associating with magnetic force. And in physics, we measure the magnetic force with what type of units? Yes, that's actually a thing, right? So that's 1/2 of a newton. 1/2 of a newton. In America, we use pounds. You could think of newtons as being the equivalent of pounds, right? Maybe in some parts of the world they stand on a scale and it tells them how many newtons they weigh. So that represents so if these 2 magnets are exactly 2 centimeters apart, that's the force that you would feel pulling the magnets together, right? Now, if the distance is increased from 2 centimeters to 6 centimeters, then the force is going to change, right? So now the magnets are further apart. They're 6 centimeters apart. The distance between the magnets has been tripled. What's the force between the magnets now?
Newtons.
Yeah. So the first thing you should be thinking is, well, what does the formula say? Square the input. Since everybody knows that 6 squared is 36, and since everybody knows that 2 and 36 are both divisible by 2, short of turning it into a decimal, that's as good as it's going to get. 1/18 of a Newton. Is 1/18 bigger or smaller than 1/2? And if you've ever played with magnets as a kid, then that should agree with your intuition. If the magnets are close together, that you can feel there's a pull, right? If you put them far apart, you can't even feel the pull. There might be a small pull there, but you can't even feel it, right? The magnetic pull has decreased. So this does seem to agree with at least my experience with magnets. Now, this question, though, is asking for the average rate of change. Right? Of the force. So when we change the distance, the force changed, right? So we want to kind of be able to get an idea of like the relationship between a change in distance and the change in force, right? That's what the rate does for it. Does for us. Of the force, I think this language isn't used in the question, but often I'll use this language and I'm running the test next week. You might say, with respect to, okay? And that's not just the way I say it. That's pretty standard in math and in the sciences. Okay.
So we're calculating like how much change is in between each centimeter?
Mm-hmm.
All right.
Yeah. So what we're going to do is we're going to look at how much the force changed. We're going to look at how much the distance changed. Then we're going to turn that into a rate. Okay. So rates is a really great way of being able to compare things. Okay. So what we're going to do, and this might be a new symbol. This is from a letter from the Greek alphabet. This is also used a lot in math and in science. Triangle, also known as delta. We're going to subtract the forces, and that'll be the amount that the force changed by. So delta, you could just say it's like difference or subtract, right? If d is for distance, I'm going to see how much the distance changed by. And by dividing, I can see the rate at which the force changes for each change in the distance. So every problem that you do in section 1.3 is going to involve 4 numbers, subtracting 2 pair and then dividing. Okay, and that's going to be a rate. In this particular case, what 2 numbers am I subtracting in the numerator?
6 of the force of the distance of 6 centimeters minus the force of the distance between 2 centimeters.
In fact,
That's,
that's what I'm going to do in the denominator.
force would be 9/18 newtons to 1/18 newtons.
Yeah, and before I write it down, I want you to think about this. Because when you're subtracting, the order is important, right? Is it more appropriate to put 1/18 and 1 over 2?
Another way.
Or 1/2 and 1/18?
1/18 minus 1/2 because you got to have them lined up.
Right. So we got to be consistent, in other words.
Yeah.
I'm going to put the force here that corresponds to that distance. And the force here that corresponds to that distance, right? So here's another place where somebody might lose some partial credit next week. You know what I mean? If you're not consistent. See that? Now, quick quiz. What are the units for this number?
That's a, no.
That was 2 over 36.
Newtons.
Newtons.
Oh,
Newtons. And when you subtract newtons from newtons, what do you get?
Newtons.
Newtons. You subtract centimeters from centimeters, you get?
Centimeters.
So when you take newtons divided by centimeters, what do you get?
Newtons per.
Newtons per centimeter.
Yeah.
8%.
Newtons per centimeter. So our rate, our final answer will have units. And the units for that number are going to be newtons per centimeter. Denominator is the easy one, right? This is a good chance to review that pre-calculus stuff. Like how do you subtract fractions?
Yeah, find a common denominator.
Common denominator is the key, right?
Yeah.
What's the least common denominator between 18 and 2?
9.
Okay, 18.
Yeah. 2 goes into 18.
Right.
So I'm going to need to modify this fraction so that the denominator is also 18. How do you do that?
Times 9, the numerator and the denominator.
Yeah.
9 over 18.
Once you have a common denominator, how do you finish it off?
You're going to subtract.
Yeah, but just subtract the numerator. Don't subtract the denominators. That would be a mistake.
Yeah.
You'll find you'll have lots of chances to practice that, a lot of that pre-calculus. 1 minus 9 is? So the numerator is going to be negative. Pro tip, the length of the division line is crucial. Yeah, so this is, by no means is this the only way of doing it, and nor is it like the best way to do it. It's just the way I felt like doing it today. So yeah, let's see here. So there's a couple things I could do here. I mean, like for example, the 8 over 18, I think I can simplify that.
Right.
They're both divisible by 2. We also need to divide the whole thing by 4.
Right.
So it's worth noticing that the division by 4 is, one could say it's like you're dividing by the fraction 4/1. And division by 4/1 is the same thing as multiplication by.
1.
Yeah. So this is the same thing as -8/18 times 1/4. And I'm thinking since 4, since 4 goes into 8 twice,
Yay.
and since 2 goes into 18,
Once or twice, 9.
9 times, yeah.
I'm thinking of 1. 2 goes into 1 one time.
Then my answer is -1/9. On a calculator, I think that would be -0.111.
Newtons per centimeter.
Right. But the most important point is that the units are in newtons per centimeter.
A moment ago, you said the length of the line that divides the fraction, that I forgot what it's called, that was important. Can you
Yeah.
elaborate?
Yeah, so the fact that this is a short line and that's a big line makes it crystal clear that what you're looking at is a fraction within a fraction, but in particular, that the numerator is a fraction. As compared to
So you don't get confused.
something like this,
Okay, I understand.
right? This is also a fraction within a fraction, but now, because this division line is shorter, it's clear to me that the denominator is a fraction, right? And I think a lot of people get confused, it's like they're doing the homework, and I kind of look over people's shoulders, like in the tutoring center, and both the division lines will be the same length, and then they'll get up to use the bathroom and come back, and then like misinterpret what they wrote. So this is another case. This is like a pro tip. Make it, don't, you can see I'm really exaggerating pretty dramatically so that I don't get that detail confused, right? So yeah, so that's what I meant by the length of this division line is important. Okay. So yeah, even this one example has a lot of layers to it. There's the layer of just taking an English sentence in context and being able to like translate that into this formula or apply this formula. To review the pre-calculus to arrive at this number. But then to kind of bring it back around full circle to the original question, which is, so what? What does that have to do with magnets? What does this tell me about magnets? Right? It helps that I have the units. But notice that the fact that there's a negative here, sometimes you'll get a rate that's positive, sometimes you'll get a rate.
It's decreasing.
Right. Positive or negative. Different things going on. There, keep track of time. Oh, okay. I got 1 more minute. All right, good. So when the rate is positive, then that tells you that both delta F and delta D are changing in the same way, right? So if D increases, then F increases. And vice versa. If D decreases, then F decreases, right? Now, when the rate is negative, then that means that the two things that we're comparing are changing in the opposite. So the fact that we got a negative number here tells me that if I increase the distance between the magnets, then that's going to decrease the force. And vice versa. If I was to decrease the distance, that would increase the force. Does that make sense? So I like to ask these interpretation questions, like that negative is almost more important than the 1/9 itself, right? But the 1/9 is also telling me the rate at which it's changing. In a sense, you could say it's for every 9 centimeters, it's going to change by 1 newton. You could say, or expressed as a decimal, I could also say, for every 1 centimeter, the force changes by about 0.11 newtons. That make sense?